Hello and welcome to a new video on the CryptoTool YouTube channel. In this video I want to show you what a perfect cipher is and what the OneTime Pad is. I structured this video into different topics. First we want to discuss what is a perfect cipher, and then I want to show you the OneTime Pad in detail. And after that I have a more or less funny topic, and I want to show you that you can create a perfect cipher using the Caesar cipher. As with all videos in this series, I first show you where we are currently now in the cryptology. So, as we already know, cryptography is the art of making ciphers and cryptanalysis is the art of breaking ciphers. And our topic today is cryptology, cryptography, modern cryptography and symmetric cryptography. And the OneTime Pad is a symmetric encryption algorithm. What is a perfect cipher? First of all, we need some sets, and our cipher has a set of plaintexts M, a set of ciphertexts C, and of course a set of keys K. The definition of a perfect cipher is that the a priori probability of the plaintext message M, element of the set of plaintext messages, is the same as the a posteriori probability of the plaintext message M given the corresponding ciphertext C. So what does this exactly mean? This means that the ciphertext provides no information at all about the plaintext. So I made two examples here that you see what a perfect cipher is and what a perfect cipher is not. On the left side we have first the perfect cipher system. It consists of two possible plaintext messages and two possible ciphertext messages and two keys that can be used to come from plaintext to ciphertexts. And you use K1 on P1, then you get C1. And if you use K2 on P1, you get C2. And in contrast to that, if you use the K2 with P2, you go to the ciphertext 1. And if you use the K1 with P2, you go to the ciphertext 2. And now we assume that these two plaintext messages here have the same probability. So with two plaintext messages, the probability for this plaintext message is exactly half. And here the same. So that was the a priori probability of a plaintext, which is for both plaintexts equal to 0.5, so a half. And now when we receive a ciphertext message, what is the a posteriori probability for such a plaintext? So let's assume we received C1. And of course we assume that the probability for the keys here is also 0.5. So when we received C1 with 50% probability, it was P2, and also with 50% probability, it was P1. So we don't know when we received C1, was it P1 or P2? And the same, of course, applies to C2. We don't know, was it P1 or was it P2, because both have the same probability. So this is a perfect cipher system. You cannot know what exactly was the original plaintext if you don't have the correct key. And now we have a non-perfect cipher system here. It's just an extension of this system here, but instead of two plaintexts it has three, and instead of two ciphertexts it has also three. And of course we have three different keys. And here you can see the problem with this cipher system. When you receive the ciphertext 3 here, then with 100% you know it was the plaintext 3, because there's no possibility to encrypt P1 or P2 to C3. And this is a non-perfect cipher system. So let's come to the OneTime Pad. The OneTime Pad was invented by Frank Miller in 1882, and he suggested to super encrypt a codebook cipher he invented using random numbers. And this super encryption is a OneTime Pad. In 1917, Gilbert Vernon registered the idea as a patent. And then finally in 1918, Joseph O. Maubourn implemented the idea and named it finally OneTime Pad. You have the three inventors of the OneTime Pad here on the right side. So this is Frank Miller, this is Gilbert Vernon, and this is Joseph Maubourn. And the basic idea of the OneTime Pad is to use a random key stream to encrypt and of course to decrypt a message. And this is so-called stream cipher. So we had already videos how stream ciphers work. So if you're interested in the basic ideas of stream cipher, I suggest you to have a look at this video. And what are the requirements for the OneTime Pad? The OneTime Pad has three requirements. First, the key stream has to be a true random key stream. So you cannot use a pseudo-random key stream to generate a real OneTime Pad. It has to be true random key stream. We will have a video about pseudo-random numbers and true random numbers probably in the near future. But right now we have just to assume that we can generate true random numbers that we use for a true random key stream. Then of course the length of the key stream has to be equal to the length of the message. So for each of the letters of the message we need a different random number. How the OneTime Pad works we will see on the next slide. And then in the end the key stream must only be used once, and that's why it's called a OneTime Pad. So if you reuse the key stream to encrypt a different message, you come into big trouble, and we will see this in the live demonstration when we have a look at the OneTime Pad in CrypTool 2. So how does the OneTime Pad works? The OneTime Pad works as follows, and we use here binary data, so only ones and zeros. And when you want to encrypt text, the text has to be converted to binary. You can use the ASCII code or you can use the Bodeau code. And in fact, Vernon used the Bodeau code when he invented the Vernon cipher. Here we have now an example. We have a plaintext which consists of zeros and ones. So this is a binary encoded text. Then we have a randomly generated key stream here. And finally, we have our output here. And so how does the cipher work? You take the plaintext, you take each bit, and you XOR the bit with the key stream bits. We already know how the XOR operation works. We saw that in the last videos. And finally, you get the result here. For instance, 0 XOR 0 is 0. 1 XOR 1 is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1, and so on. And when you want to decrypt on the receiver side, you take the ciphertext. You have to have, of course, the same OneTime Pad, the same key stream here, and then you go backwards. You encrypt by using 0 XOR 0 is 0, 0 XOR 1 is 1, 0 0 0, 1 1 is 0, 1 0 is 1, and so on. And as you probably already have seen, is this graph here is the same that I have already shown you, but here now we have ones and zeros instead of P1, P2 and so on. And we have for the keys also 0 and 1. In fact, this here is the XOR operation. And performing the XOR operation on a single bit is a perfect cipher. Because when we receive a 1, we don't know was it a 1 or was it a 0, because of the same probability it could have been a 0 or 1. And so the XOR on a single bit is a perfect cipher. And also when we extend the XOR on arbitrary length of streams of bits, and of course we use a random key stream with random generated bits, we also get a perfect cipher for the complete OneTime Pad or for the complete encrypted text. Now I said we have a fun part in this video here, and the fun part is that we can actually build a perfect cipher using the Caesar cipher. And the Caesar cipher can be modified to create a perfect cipher. And remember, the Caesar cipher shifts the plaintext letters by an offset. And the key is the offset or shift value. So for instance, when you have in plaintext an A, and you shift it by 1, you get an B. You shift it by 2, you get an C, and so on. And you do it for each letter of your text. That is a Caesar cipher. And what is a perfect Caesar cipher? A perfect Caesar is that we just use a Caesar cipher with only a single letter. And yeah, we can argue now how many information you can send. In fact, you can only send 26 different messages, A to Z. But of course, you can assume that you use these messages as code words, you can say. For instance, A means attack the enemy, B means fall back, C means we need supplies, and so on. And here's a proof that the Caesar cipher is a perfect cipher. So we assume that we received a single Caesar encrypted letter, for example, the letter Z. And now, how could the Z be, what could be the plaintext for the letter Z? X could have been an A shifted by 25. So if you shift the A 25 times, then you get the letter Z. When you shift B 24 times, you get the Z. when you shift C 23 times, you get the Z, and so on and so on and so on. And finally, the Y shifted by 1 gives you a Z, or even the Z shifted by 0 gives you a Z. So if you receive a Z and you don't know the key, you don't know what the original letter was. And we can do this step here not only for a received letter Z, we can do this for every possible ciphertext letter that we receive. So regardless if we receive an A and B and C or a Z, we don't know what was the original plaintext letter. And the problem is that the a priori probability equals to the a posteriori probability. So that means that the single letter Caesar is a perfect secure cipher. The problem is, of course, you have to stick to a Caesar only with a single letter. When you use more than a single letter, then of course you can apply frequency analysis and so on, and you can decrypt. But a single letter Caesar is a perfect cipher. And another perfect cipher that you can easily create is when you use the Vigenère cipher. And you can use the Vigenère cipher with a key that is randomly generated, and the keyword has the length of your plaintext message. And in fact, this is also a OneTime Pad, but not created with an XOR operation, but created with a Vigenère cipher. Now we have different tasks with the OneTime Pad. The first task is that we want to encrypt and to decrypt using the OneTime Pad in CrypTool 2. Our second task then is to generate arbitrary correct messages using wrong pads. So the problem with the OneTime Pad is that when you don't have the correct pad, you can generate arbitrary messages using arbitrary pads. So instead of hello world, you could generate a text with the same length but different meaning. And then finally the task 3 is that we want to use the OneTime Pad key stream, or the key, twice. And that is something that you should never do, and we will see why we should never do this. I'm here now in CrypTool 2, and the first thing that I want to do is to encrypt and decrypt using a OneTime Pad. To do so, I search for a template. And we have different OneTime Pad templates, and here, for instance, we have the XOR cipher, which is also the OneTime Pad. And what do we have here? First of all, we have a text input, which is a plaintext. And then we have the key here. Let's assume that this key here was randomly generated, but we can also exchange that here with a random number generator later on. Then the first thing that will happen, our message here will be encrypted using this pad here with the XOR or the OneTime Pad cipher. And after that it will also be XORed again with the same key, and we should receive the decrypted ciphertext. Actually, this is decrypted plaintext. And we should see here the ciphertext. So let's test it. And as we can see here, we have our plaintext. This here is our ciphertext as hexadecimal values. And when we apply 2 times the XOR with the same key, of course, we get the decrypted plaintext, the original plaintext. And now let's add some random numbers to this template here. So we have the random number generator, this here. And I remove this and this. And we can set this, for instance, to random. This is a C# random method that we can use. And I connect it to the XOR here. Our output is a byte array. The seed is not important right now. Seed is when you use a pseudo-random number generator, then the seed is used to get a starting value for your generating algorithm. And if the seed or the starting value is the same, you get the same random, you can say random bits, or your same pseudo-random bits. But if you omit the seed here, it uses a randomly chosen seed automatically. So we have to change this to byte array, and we have to change this. We have here 7 characters. These are also 7 bytes, so we need a seed, not a seed, an output length of 7. Now let's test it. And it generates random numbers, as you can see here. And when I stop and start it again, it generates new random numbers. And every time Our ciphertext, of course, looks different because we generate different random numbers, but of course we always get the decrypted plaintext. The next thing I want to show you is how you can generate arbitrary messages using the OneTime Pad. And I think that in the OneTime Pad Demo you should see this. Yes, this is a nice template with different OneTime Pads. So we have here our plaintext message, attack at dawn, and then you have different OneTime Pads, so different key streams that are applied on this message. And the message is first encrypted here with the OneTime Pad 1, and then of course it's decrypted again with OneTime Pad 1. So these messages here should be the same. But also the encrypted message with OneTime Pad 1 is decrypted with this OneTime Pad 2, and that we will see here. And it's also decrypted with the OneTime Pad 3 that you will see here. So let's test it. So our original message is encrypted to this here, so it's just some random garbage. But it can of course be decrypted with the correct OneTime Pad to attack at dawn. And since it's a OneTime Pad and we can generate arbitrary messages, you can decrypt the same ciphertext with a different OneTime Pad to retreat at 11:00 or the cat is dead. And yeah, that's the nature of the OneTime Pad. You don't know what the original message was, so you generate some bits, and you can of course generate some bits that give you, when you XOR your ciphertext with these generated bits, to arbitrary messages. And in fact, you can generate every sentence that has exactly 15 characters here. So there's no way, even if you want to brute force a OneTime Pad, to find the correct message. Of course, if you try every possible bit combination here, every possible OneTime Pad with your ciphertext, you get all possible messages. You of course will see one time the attack at dawn, the correct message, but you don't know that this was the correct message. You will also see retreat at 11 or the cat is dead and every other possible message. So this makes the OneTime Pad really a perfect secure cipher. You don't know what was the original message unless you have the original OneTime Pad. And now finally I want to show you what happens if you apply a OneTime Pad keystream twice on different messages. For this we have the OneTime Pad misusage template here. And what will happen here? So we have a plaintext message here, that's plaintext A, and a plaintext message B. A is just a picture that is encrypted using a binary stream, a OneTime Pad, and B will be also encrypted using the same OneTime Pad. And then you will see a ciphertext A here, and when you apply random numbers or random keystream on a picture, you should just see white noise. And here you should also see only white noise. But what we do here is that we XOR both white noises or both ciphertexts on each other. And then you will see here ciphertext A XOR ciphertext B. And when you remember the XOR operation, when you have two messages XOR the same key and you XOR both, then you completely remove the key. And what you get is the A message XOR the B message. So I will just start it and then you will see what I mean. So here we have the A picture, here we have the B picture. And here you have the ciphertext A, it just looks like random noise. In fact, it's random noise. If you don't have the correct key, then you don't know what it is. And here it's the same. But since in both of these messages you have the key, when you XOR these, you get this here. And here you can see that you can see both messages. You have the A and you have the B. And the problem is now, when you do this with text, you have a text encrypted with a OneTime Pad, one text, one plaintext message, and you have a second plaintext message encrypted with the same pad. Then of course you get the combination of both texts. But you can then guess one of the texts, and then when you guess the correct text, you get the other text also correct. And that's a problem here. So you should never apply the same OneTime Pad on two different messages, because then you can remove the key. And with these pictures here, you can see it very well. Yeah, and this was everything that I wanted to show you with OneTime Pads and perfect ciphers. So keep in mind when you implement OneTime Pads that you use only key stream once. So after using a OneTime Pad, you just throw it away. Otherwise, you have really big problems. And there's another problem with OneTime Pads. That's why we don't use these right now, for instance, on the internet. The problem is that you have to take the key to the receiver before you send him the text. And in fact, in history, this was used. So secret agencies sent their spies with cases consisting only random numbers from one country to another, so that when they wanted to communicate, that they can use both the same OneTime Pad on each side. But of course, for using this as an encryption in the internet, you don't want to go to Amazon and then take the OneTime Pad to your home that you can communicate in a secure manner with Amazon. That's a practical problem with the OneTime Pad. But despite these practical problems, the OneTime Pad is really a perfect cipher. And if you need a cipher for such high security that you need a perfect cipher, then of course you could use the OneTime Pad. Okay, once again, thank you very much for watching this video. If you're interested in more, please subscribe to our channel. Give a thumbs up if you like this video. If you don't like it, give a thumbs down, and see you in the next video.